At the molecular level, chemical substitution occurs in high-energy environments. Structures are constantly colliding, breaking, and forming bonds to reach a more stable state. Within an alkane framework, the process targets a central carbon atom. Attached to this carbon is a halogen atom. We categorize this as the leaving group because it is the component being replaced during the reaction. The reactive agent seeking to bond with the carbon is the nucleophile. The fundamental goal is simple: exchange the halogen for the nucleophile. While the objective is constant, the physical path the atoms take depends entirely on the architecture surrounding that central carbon. We can see this divergence by comparing a primary carbon on the left with a tertiary carbon on the right. The primary carbon is attached to only one alkyl group. With only small hydrogen atoms occupying the other bonds, the central carbon is relatively exposed. The tertiary carbon is surrounded by three bulky alkyl groups. These substituents physically encase the central atom. In an Sn2 reaction, a single-step substitution, the exposed primary carbon reacts rapidly. However, the tertiary carbon's reaction rate for this same mechanism drops to 0. We see the opposite trend in an Sn1 reaction, which involves two steps. The primary carbon fails to react, while the tertiary carbon executes this pathway efficiently. While the primary carbon completes its substitution in a single motion, the crowded tertiary carbon follows a multi-step sequence to achieve the same result. This preference for the Sn1 pathway is a requirement dictated by the specific interaction between steric hindrance and carbocation stability. A single-step Sn2 substitution relies on a specific geometrical alignment. To bond with the carbon, the nucleophile must perform a backside attack at exactly 180 degrees, opposite the leaving halogen. When we look at the tertiary haloalkane using van der Waals radii, we see the actual spatial footprint of the three methyl groups. The volume these groups occupy creates a physical barrier known as steric hindrance. As a nucleophile attempts the 180-degree backside attack, it enters the space occupied by these alkyl groups. The electron cloud of the nucleophile begins to repel the electron clouds of the three surrounding groups. This repulsion prevents the nucleophile from reaching the central carbon. The physical trajectory is blocked before a new bond can even begin to form. Steric hindrance renders the Sn2 pathway physically impossible for a tertiary carbon, forcing the system to find an alternative route. Because the direct attack is blocked, substitution can only begin if the leaving group detaches on its own. When the halogen bond snaps, it takes both bonding electrons with it, leaving the carbon framework incomplete. The result is a carbocation, an intermediate state where the central carbon carries a full positive charge. To minimize electronic strain, the three alkyl groups repel one another into a single plane, shifting the framework from a 3D tetrahedron to a flat 2D geometry. Maintaining a positive charge on a single carbon atom is typically too unstable for the molecule to survive. However, the tertiary structure utilizes the inductive effect, where the three surrounding alkyl groups shift their electron density toward the center. This inward donation of negative charge stabilizes the positive center, providing the electronic scaffolding necessary for the intermediate to exist. The same bulky groups that physically block the Sn2 attack provide the electronic stabilization required for the molecule to proceed through the Sn1 pathway. This stabilized flat intermediate is known as a trigonal planar carbocation. Because the structure is flat, an unoccupied p orbital extends above and below the plane. The nucleophile returns. With the steric barrier gone, it can attack from the top or bottom, making either path equally likely. This trigonal planar geometry creates a perfectly split probability, removing the strict 180-degree restriction found in the Sn2 mechanism. If the nucleophile bonds from the top, it produces a molecule with one specific spatial orientation. An attack from the bottom produces its exact mirror image. The result is a perfect 50-50 split of mirrored molecules, a racemic mixture. This contrasts with Sn2, which always produces a single inverted orientation. Detecting this mixture provides empirical evidence that the reaction proceeded through a flat intermediate. The tertiary carbon is governed by its physical volume, which creates a blockade against concerted attacks. Simultaneously, it is enabled by its internal electronics, which allow it to survive a multi-step sequence. Deliberate pacing. The tertiary carbon's preference for Sn1 is the result of its molecular architecture. It follows the only physical path that its structure allows.